Hello, my name is Jeerpon Singh Nongban.
And my name is Titipong Randet.
We're proud to present about our project, a novel floatable painting material for inner mangrove forest inspired by Barringtonia asiatica. Mangrove forests are one of the most important ecosystems on Earth. But did you know that in the last 50 years, the mangrove forest areas has decreased by as much as a quarter from all over the world? Just think about the big consequences that would have. Recently, people have been trying to restore the mangrove forest. However, most of these people prefer to restore the outer mangrove forest areas because they are easier to access, whereas repairing the inner areas require breaking to the dense roots of plants. This causes plant tramping and can be dangerous too. This point made us wonder how we can restore the inner plants when they die, and it leads to our project.
And first, to find a suitable area for our case study, we started by exploring the mangrove forest in Thailand with satellite imagery because we want to know what the characteristics are of mangrove forest in Thailand. We studied 10 areas, 5 placed in the West Coastal or Andaman, and 5 in the East Coastal or the Gulf of Thailand. And we found that in Chanthaburi province, 39.76% of the inner area is open space and the outer is dense with root of tree, making it difficult to restore. So we decided to use this area for our experiment.
And from our field research, we observed the garbage that was floating in the mangrove forest area. So this is our inspiration. We have an idea to create an object that can float into the inner mangrove forest to plant a tree. The next question that we wondered about was whether the shapes of the object will affect the ability to float or not. So we designed an object in three geometric shapes, but we found that all three shapes has a rotational behavior that we can control, which affect the seed germination. When we were doing some experiments, we found that our geometric shapes doesn't suitable at all. So we try to observe the surroundings more and more. Later on, we encountered the fruits of the plant called the Barringtonia asiatica, which can return to an upright position after it overturning. We wonder how it can do this, so we collect all of the Barringtonia asiatica fruits that we could find at that moment to study its external and internal structure. We found some interesting things like the inner texture is like a sponge and lightweight. Also, the fresh fruits has a harder texture than the dried fruits. In addition, the bulk of the fiber for about 20% is packed at the bottom of the fruits and it also has seed weight of up to 60% of the fruits. For these reasons, Barringtonia asiatica does not overturn when floating in the water, or in other words, it's in a stable equilibrium.
Therefore, we have used the structure of Barringtonia asiatica as model for developing our floatable planting material. We mold our object as sponge fiber from latex, and we add nutrients that are important for sapling from the agricultural waste as bagasse and soybean meal. The study was conducted at variance ratio 1:0, 1:3, 1:1, 3:1, and 0:1 of bagasse and soybean meal. And we found that the 1:1 ratio of bagasse and soybean meal had the most suitable characteristic because it enabled the planting material to float and the porosity is 40.26%, which is a good percentage for the material. And next, we study degradation of our floatable planting material. The degradation test was performed under the variant condition, bury in the soil and dip in the seawater for 90 days. After 90 days, our planting material had a zero degradation. It degraded in soil by 16%, in seawater by 9%. And we found that the volume of latex and the chemical used in the molding process were decreased. So we created a new version. We reduced the volume of latex from around 50% to less than 3%, and we didn't use chemical at all because we want our planting material to be an environmental friendly product. After we improve our planting material, we study degradation again, and we found that our planting material degraded in soil by 27% and in seawater by 80%. Then we wonder, What would be the results if we use our planting material to plant a tree? We use a species of mangrove tree called Avicennia alba because this type of tree is a pioneer species and it can grow easily in mangrove forest. We found that after 90 days, Avicennia alba was 40.70 centimeter tall and had 80 leaves. It can grow better than the natural planting by 9.7%. After that, we study its environmental impact in order to make sure that the innovation we made had a positive effect on the environment. We also examine the chemical property of the soil and seawater after our planting material has decomposed for 90 days. We found that the organic matter in soil increased from 1.5% to more than 3.5%. BOD level increasing from 1.45 mg per liter to 2.11 mg per liter, and EC increasing from 5.1 millisiemen per centimeter to 7.6 millisiemen per centimeter.
And from the reason that we are the group of the people that like playing games, so we became interested in the idea of developing a model from the game that can help us observe the floating behavior clearly and can answer our questions before test in field. Therefore, we study the flotation condition in the laboratory by making a CFD simulation in Unreal Engine 4. We have set the factors such as the waves and the environments in the simulations as realistic as possible by collecting data from field and from the coastal resource department. And from the simulation, we found that the good distribution ratios per percentage of open space was 1:2, and the material can distribute it in all areas. After doing all of this preparation, we were finally ready to test our material in the field. When we released our planting material into our experimental area, we found that the planting material was able to float in the inner mangrove forest area. We released it from 20 units of the floatable planting material from 5 different points, and we found that the planting material can float through the inner mangrove forest area successfully for 100%, within a distance of 100 meters would take an average of 63 minutes. And when we surveyed the mangrove forest 3 months after we had done all of the experiments, we found that all of the trees that we managed to observe were still growing successfully.
And next is conclusion. We had 5 points in this topic. First, the mangrove forest situation is decreasing in many provinces in Thailand, including Chanthaburi province. Second, the structure of floatable planting material had an effect on the direction of plant growth, and the structure of Barringtonia asiatica is more suitable than 3 basic geometric shapes. Third, the optimal ratio of bagasse and soybean meal create a suitable porosity for the material. This affects the flotation and the growth rate of plant. Fourth, the plants in our planting material was able to grow, and it can continue to grow as they enter in the mangrove forest. And our planting material is biodegradable in soil and water, and it helps increase the organic matter in soil as well as the EC BOD level in water too. And the last, floatable planting material can float into the target area, both the laboratory and the field with good distribution.
To sum up, we created an innovation that has a high potential for real-world use. Our innovation can restore mangrove forests, which will help to create a better world by contributing to environmental restoration and sustainable economic developments, corresponding to the Sustainable Development Goals and Thailand Biocircular Green Economics Model. Thank you.